Okay, so today is the last lecture, and this is going to be on the small world phenomenon. This is chapter 20 in the text. So this originates kind of from the idea of the 6 degrees of separation, and that individuals and groups within social networks are connected to each other via very short paths. And there's the famous saying 6 degrees of separation that was based on the study by Stanley Milgram. That was where they had people mailing a letter to a person who is living in Sharon, Massachusetts. I believe that person was a stockbroker, and roughly 1/3 of the letters were successful, and the median number of steps they took there to get there was 6. So that's where the 6 degrees of separation comes in. Milgram's experiment revealed that short paths exist in abundance in social networks, and people are able to successfully find these paths based on both geographical and occupational features. So these are kind of compatible with our intuition. If you think about yourself and you say 100 people, the number of people should grow exponentially with each step out. So 100 people, and each of them knows 100 people. So you're at 10,000 by the time you get 2 steps out. However, that's going to be limited a little bit by triadic closure. And triadic closure was something we discussed earlier in the class, where you're friends with a friend who is friend with somebody else. There's a likelihood of that forming a triangle friendship where the 3 are friends with one another. That's the triadic closure. So that will limit things a little bit. And the other thing to notice is it appears locally clustered, but it's actually highly branching. So Watson and Strogatz went out to make a model of it with many closed triads, but also with very short paths to see how this can actually happen. It was based on homophily, which is, we have a tendency to be like our friends, but it also incorporated weak ties. So in their model, everybody lives in a 2-dimensional grid. 2 nodes are a grid step apart from one another if they're up or down or right or left of one another. And the homophily is captured by having each node form a link with all the other nodes lie within a radius of up to r grid steps away. And weak ties are modeled by having some other constant value k. You'll have k weak ties that'll form a link to k other nodes that are selected uniformly at random throughout the grid. So it works because if you're starting in node V, then using only the k weak ties out of each node, you're likely to get farther, and then you can use those individual local ties. And since these links are chosen uniformly at random, we're very unlikely to ever see a node twice in the first 2 steps outward from V. And there's only a small amount of randomness that's actually needed to make this work. You can think of these subsquares as towns or islands in the case of Hawaii. So, for example, if you were looking for someone in Hana, you could use a weak tie to jump over to Maui and start searching from there if you wanted to find that person. So this is an idea called social search, and that's another aspect of Milgram's experiment. If we want the absolutely shortest path between the people that we could find, we would use breadth first search. You check with each of your friends, they check with each of their friends, etc. But that's not really practical for what we're doing here, social searching. In terms of trying to find the stockbroker, and it might end up annoying all our friends as we collected this massive address book. So Milgram used this analogy of tunneling. So we started out in Omaha, and we want to get to Boston, or a suburb of Boston, Sharon, Massachusetts. And what we can see is we make some long jumps at first from 1,305 miles distance to 710 somewhere in Ohio, to somewhere in, looks like upstate New York, perhaps, which is 356 miles, maybe over to New Hampshire or Vermont. And then we gradually close in on the target person. So we can actually make a model to see why this decentralized search is effective. And, if we start with Watson and Strogatz, we can think about a node S who needs to forward a letter to T. S doesn't know the random edges out of any node other than S itself. Again, that's because we can't contact each one of our friends and say, hey, who do you know? So we only know, the people that we can send it to. And, we can evaluate, how well this performs based on delivery time. But Watson Strogatz is insufficient to show, since it's very hard to use the weak ties here to close in on something. What we need to do is reduce the distance at each step to make a progressive closing in. So what we do is we add an extra quantity that controls the scale spanned by the weak ties. Each of the nodes k random edges is generated in a way that decays with the distance using a clustering exponent q. And this makes sense to us naturally. We're more likely to know people here in the islands. As you go further away, you'll have fewer and fewer ties. So you're more likely to know several people over on Oahu than you would be to know say several people in New Mexico, and that makes intuitive sense to us. In generating a random edge out of B to W, we have this edge link to W B with probability proportional to the distance between V and W raised to the minus Q. If Q is equal to 0, we get that randomness. That can be any distance. Q equals 2 ends up being the most efficient due to scales of resolution. For example, from 2 to 4, 4 to 8, 8 to 16, the powers of 2 moving out that way. So the probability of a link in the 2D range is independent of D at Q is equal to 2, and that's why 2 works really well for Q. When Q is equal to 2, weak ties are being formed in a way that's spread out uniformly across different scales of resolution. So you have some at the 2D distance, some at the 4D distance, etc. And empirical studies support this Q is equal to 2 finding. A live journal study that looked at 500,000 users who provided a zip code showed this, but one problem with that is that the US population is not uniformly distributed. So you have a lot of people on the East Coast in that I-95 corridor, a lot of people on the West Coast in that I-5 corridor. Things are more spread out in the center of the country. Particularly, after you pass probably, Chicago, things get very spread out in terms of people. So instead of using Euclidean distance, we can use rank. That is the number of other nodes that are closer to V than W. So here, W is rank 7 because there's 2, 4, 6 nodes between V and W. There are 6 nodes that are closer to V, so W has rank 7, and that's how we can figure out the rank. If random links are constructed using this rank-based friendship with exponent 1, the resulting network allows for efficient decentralized search with high probability. And live journal data actually ended up being 1.1, so that's pretty startlingly close. And the results were corroborated through a study on Facebook, or Meta as it's now called. So we've got this close alignment of theory and measurement. And why have real social networks arranged themselves in a pattern of friendships across distance that's close to optimal for forwarding messages to faraway targets? Not something we're necessarily intentionally doing, but Sandberg conjectures that over time, the network kind of begins to adapt to the pattern of searches that you're trying to accomplish with your social network. And eventually these searches will become more efficient. So another reason that social search is efficient is due to social foci, and these are the shared activities, communities, common pursuits, things like our karate club that we introduced way back in chapter 1. And these provide a flexible and general way to produce models that exhibit an abundance of short paths and efficient decentralized search. So what we want to do is focus on the size of the smallest social. The social distance between two people is the size of the smallest focus that includes both of them. When nodes link to each other with probability inversely proportional to that social distance, the resulting network is efficiently searchable. And again, exponent p equal 1 is the natural generalization of that inverse square law for the simple grid model. The Milgram experiment was designed to test the hypothesis that people are connected by short paths in the global social network, but it also serves as an empirical study of people's ability to collectively solve a problem. How do you get a letter from Omaha, and this is back in the 60s or 70s, to a stockbroker in a suburb of Boston? And basically people aren't aware that they're necessarily collectively working to solve that problem. So, some strategies are move closer to the target geographically, and find friends who are the most connected so that they can reach out. You don't want your friend that doesn't talk to anyone to be the one who forwards the letter, because it likely won't go anywhere. And that's a limitation, is lack of participation. Not everybody's going to try. Particularly you see this in surveys in the social sciences. So you have to take into account the response rate, but you can assume it's fairly representative of the population of the whole. And you might have to do some stretches for that, but assuming you can do that, then the results will hold. Reaching the target is actually most successful when the target is affluent. And that's because high status people are linked into a densely connected core. Think about forwarding something all the way over to North Korea. You're probably more likely to reach Kim Jong-un than you are to reach somebody on the periphery in a small town. That's because low status people are atomized around the periphery of the network. So that's it. That wraps up chapter 20. Thanks so much for listening.